Minasan, konnichiwa, Zamurai Engineer desu. In this module on chapter 2, this is subtopic number 3. We will discuss how to derive the forward difference approximation from Taylor series. So let us recall the Taylor's theorem that says that if you know the value of the function f at any x I as an x of I and all its derivative at that point, all its derivative meaning first derivative, second derivative, third derivative, and so on. At that point, we have to know that the derivative should exist at that point, provided the derivatives are continuous between xi and xi plus 1. So xi and xi plus 1 are the extremes, are the extremities of our domain. So if that is the case, so our what derivation is valid within that domain. Okay, take note of that important condition. Okay, so we have what first equation here is the Taylor series. Substituting for convenience, delta x is equal to xi plus I minus xi. So this is just equal to what? That is just equal to delta x is equal to x plus delta x minus x, and that is delta x. Okay. Okay. That is just for convenience. So because of that, we can what? Immediately what? Simplify the writing. The writing. It's better to write it simpler. So the same thing, we are using the same thing, but it is written in simpler symbols. Okay. So this one, xi plus 1 minus xi is actually delta x. So this is delta x replaced by delta x. So this value, this quantity is actually delta x squared. So this one is delta x squared, and so on. So we can what shorten the writing of the Taylor series. Okay. So because of that, we can have our first derivative to be equal to this one. Okay. The first derivative approximation. Okay. You can see here. Okay. How to do that? How to do this? First derivative. Use the same equation and solve for your first derivative. If you want to solve for this function xi transfer to the other side. Okay? And all the rest of the terms transfer to the other side. That's why all the rest of the terms will become negative. And also this one will become negative. This one will become negative and will become negative. So if we divide all the terms with delta x, you will notice we have delta x here minus the second derivative, which go to the other side will become negative, or second derivative 2 factorial. This delta x divided by delta x, only delta x remaining, and so on. There are minus and so on, and minus and so on. Okay, that is the same equation, but we are what? Solving for the first derivative. In this case, you will notice that we only need these first two terms. We only need these first two terms. The third term and the rest of the term could be neglected. Okay. Okay. And if you neglected that, if you neglect that third term and the rest of the term, we'll have this following equation. It is just the definition. It's just the definition of the approximation method of what? The slope or the first derivative. That is the approximation method. And that's how we derive the forward. That's how we derive the forward difference approximation method from the Taylor series. So using Taylor series, we can do it. The third term and the rest of the term are very small because the second derivative will become smaller, and there is what? A denominator. There is a denominator 2 factorial. The fourth term of the denominator 3 factorial. So it will become a smaller and smaller amount. That's why we can neglect these terms. That is the reasoning. And we are able to derive the forward approximation method by using Taylor series. The 0 times delta x term shows that the error in the approximation is of the order of delta x. Okay? So, meaning the error is on a function of delta x, which is smaller than x. Delta x value is smaller than x because delta x is just what? A small finite value, but we can choose delta x as small as possible. Remember, okay? We can choose a value for delta x as small as possible. In our previous examples, we choose delta x to be equal to 2 seconds, which is still a large value. Actually, you can choose delta x equal to 0.2 or 0.1 second rather than 2 seconds. Imagine the error. We already have a small error when we are choosing delta x is equal to 2 seconds. What more can we expect for the accuracy when we choose delta x equal to 0.2 or 0.1 second? Imagine that. Again, for this video, your example is to derive the Taylor series formula for backward difference approximation method for first derivative. So just like we had derived it in the forward difference method. Okay, so do it. Use your ball pen and paper to derive starting from Taylor series. Derive the backward divided difference, okay, method. So as shown above, both forward and backward divided difference approximation of the first derivative are accurate on the order of quantity 0 times delta x. Can we get better approximation? Yes, we can still get better from forward or from backward. Another method to approximate first derivative is called the central difference approximation. So our next topic would be that. And I would just wait for a minute to get your clarification, questions, and other things that you would like to ask. And also you can use the comment section below for your question. Again, this is Dr. EYPEI, preaching engineering for nation building.